everybody. My name is László. Thanks for the introduction. We have a known project. We build a small size hpcResource, and I would like to introduce this resource. Last year, I'm talking about 3D city projects. I was a graduate student to visit one of the supercomputing center, thanks to the praise. And I'm working there on city segmentation and visualization. And we completely use supercomputers to achieve these goals. We segment the organ from the city slides on feed resources, and the visualization parts runs on GPUs. And finally, results that flavor which can you see on the middle of the slides. And we also work on kidneys. This is an important part for the doctors who try to solve, try to treat after surgery that the liver the cancer can infect the liver, and if we got the liver, the organ can reproduce itself. So if we detect it in time and make some operations, we can save the lives. And the question is, after the operation, who can reproduce the liver itself? Can again make cancer part, or can grow a healthy part? And during this period, the patient all the time, every half of the year, can go to the doctor and make CT pictures and check whether the state is the current state of the liver. So the conclusion was that we can reach the goal. The results will be very fine and impressive. The problem was that without supercomputers it can be manageable. So this liver, actually now this is just a picture, but there was a video and other stuff which rendering on the supercomputers in a couple of hours could be run. And this means that it is impressive, but you can't use as a real application. So how can we over this bottleneck? One possible solution, we found that one possible solution is we make a research on supercomputers, and after that we can use these results, and if we build a small size supercomputer and give to the doctor, you can use it in real time. For instance, you just plug into the CT machines, and the pictures from the machines go to directly into this small size supercomputers, and the final results will be showed after approximately 10 minutes, for example. So our expectation about supercomputer was it should be small, it should be mobile. We will see how it is mobile. It should be operated on a non-AC environment. It means it should be placed in a surgery room, not in a server room. Should be energy and performance optimized, and we would like to run some kind of applications we can utilize, of course, 900 degrees, and it should be scalability. If there is computational limitations, we could extend the computers. Last year, we received some grants, for example, from India, from National Talent Program, and there are some companies grants also, and this is the reason why we can start this project. Now we finished the first prototype, and there is a patent pending now on this machine. And what is we achieved? This is a hybrid localized computing. As you will see, okay, on the right side you will see videos about building in our whole slide. I'm sorry, there are some personal things on the pictures because it's built in my living room. What you have to note about the first prototype is contains only one compute node. Will contains 4 coprocessor cards, two different coprocessor cards, 2 MIG and 2 GPU, and it could be extended if this case is allowed to build another other computing node on the top, and there is another case where you can include in one case 2 nodes, and on the top another 2 nodes, and so on. The last video contains that really the machine gives wheels. It should be because relatively big, so it's approximately 50 kilograms for one node. This prototype contains 2 CPU integrated on the board, and this is important because this should serve 4 full PCI Express connectors to the cards, and it should be separated so that we can for all CPUs we can serve one type of coprocessor. As the cooling, we use a hybrid solution, air and liquid cooling. This is the air part. There are some air corridors in the PC case. The main idea was that the fresh air comes from below, and most of the warm air left the PC case at the top. There are some interesting signs, interesting numbers. We use very high performance ventilators. The speed is 3000 RPMs, and the static pressure is almost 60 Pascal. Of course, it can't work all the time at full capacity, but if it is necessary, it can. The liquid part cooling all the main components, CPUs. It is possible to cool RAMs, offset chipsets, and all the cards. The prototype contains only currently the CPUs and GPU and MIG card cooling, and there is 2 big radiators on top of the case. It means there is 2 parallel circuit system. One is cooling 1 processors and 2 cards, and the other one cools the others. On the videos you can see how we'll rebuild the card with cooling boards. There are some rows about the radiator. There are optional radiators. This prototype does not contains all of the possible radiators, just the 2 main ones. On the right side there is a pump and reservoir. It is placed outside from the case because there is a overpressure relief valve on top if the temperature is too high and the pump generate more pressure. It can so it release the overpressure. This is important because the cards can reach the 90 degrees temperatures without any problem. So the liquid part actually is very similar to the cooling. The cars, there is radiator, there is reservoir, there is pump, and there is overrelief. There are other interesting things that you have to, if you build this type of computer, you have to place some kind of material to help to go the warm to the water cooling part. This is a cooling pads. We use almost general ones. It's we plan to replace it relatively more performance. We will see in the next slides what is the cooling performance. Here you can see how placed the cards in the computers. As I mentioned, all CPUs has all type of cards. So the first lot contains the GPU, the second one is the fee card, and so on. Because of the big size of cooling components, there are some extra modifications on cables. For instance, the USB connectors and VGA connectors can be plugged in because of the size of the cooling components. This you can see now that would be solved this problem. Okay. I forget there is two. Okay, on the top video you can see how we modified the case to build everything. And as I forget that there is two PSU components to work in this machine. One of them is for the cards and the main boards, and the other one is for the cooling parts. The first one is approximately 1700 watts PSU, and the other one is approximately 500. For one node, this is enough. Anyway, all of the components, so the cooling part and the PSU part also plan that approximately 80 degrees of the full capacity is enough to working the full computer. Okay, you can see that how the pump and reservoir fastened on the side of the case. If of course if we place the other computing nodes on the top, the radiators would be built upper than in this prototype. In the next slide, you can see that the liquid is flowing in solid tubes. Currently it is built from plastic, and there is a heat gun used to formed to connect the components. And on the left side of the picture, you can see that how it looks like the compute nodes after the cable. This is a sample cable. You can see one circle. It is colored lead. The first the liquid comes from the reservoir from the CPU. After that, go to the first card, then the second card, and go back to the reservoir and go to the radiator. There is airflow around the HDD. The HDD is stand on the right side, and it is allowed to make airflow behind among them. And here is the finishing of the computer. This is the first filling. The liquid cooling contains very clear H2O. It's 90 degrees just water, and the other stuff is parametric material. This is prevents oxidation of the components. Is necessary because all the components build metal. It is this all the water and other components is it's very low conductivity. It is necessary because if somehow happens that liquid flows to the computer, it's that there is no fire or any other terrible things. We use actually osmosis water. It's not the cleanest one, but it is well enough. And actually, after you put the clear water into the system, it will be after a couple of hours the TDS reach a little bit higher volume. It is because the water pH is very low and can dissolve relatively small iron and other stuff from the metal components. Okay, there are some pressure tests. The ideal pressure, the ideal temperature is around 35 degrees. If we full loaded the GPU card, we reach the 570 degrees, which is very good because with the original cooling components, we reach 58 degrees after 2 minutes, and the card is overheated. As we talk about, if we talk about the phi cards, we reach the 70 degrees, which is relatively high. It is because we currently can't build in the optional radiators. It means the phi cards received warmer water because the CPUs and GPUs warm the water, and this warm water try to cool the phi cards, which is enough but not the optimal. But if we build it the second or third radiators, we can reach lower temperatures. Okay, current configuration contains 130 Intel cores and approximately 6,000 NVIDIA CUDA cores without threads. The theoretical performance from the Intel and NVIDIA is the replacement side. We measured currently 300 teraflops, 1.0 teraflops with default setup, and we reached 1004 teraflops if we modified a little bit the input parameters of the testing functions, but we should know that this is this measure comes that we try to test all the cards, all the components separately. So we can't try it all the components at the same time. Okay, and this is not last slide. Last slide. Our plan now that we would like to develop hybrid computing on hybrid cards. So we would like to optimize it, spread it, the functions into the cards that it should be suitable not just for the cards but for the problems also. It means we try to separate, try to decide it in advance which functions could be run on GPU on the field card more performance. Thanks for that.
Okay, we have time for just 2 questions.
So what's the main design parameter here? The 1700 watts, so that's the top PSU you can afford in this setting, or is this that we want 1 teraflop, or what exactly is the parameter that converges on this design? I'm just curious.
Yeah, the main idea was we can use more high efficiently the hardware and the software if we use hybrid components.
No, I understand that part. If you could have built 2 such things, and then you get now, so you get something converges on this size, and I'm just curious, like what is the main parameter that drove this particular thing? You could have designed something with presumably much different CPU, more cards, right? You could have chosen something which is only half this system, but you chose this one, so there has to be some reason.
Yeah, because we would like to activate all CPUs in different cards. This is the reason why 4 card is built in. So if you check how the main board was built, you will see that all CPU has two hpcResource slots. So if you are writing a program, we can achieve that all the CPU has unique coprocessor card in all type. So you can give the task under.
So you think this is maybe the largest portable system possible?
Currently for one compute node, yes, because there is a limitation on the CPUs. There are only 40 hpcResource lanes for one CPU.
I see.
Okay, last question.
I can manage to do it without. So I drew my attention that you said that you wanted to put this computer next to a surgery. I assume it's not to a surgery room exactly, but next to it, because if you would want to put it to a surgery room, then we would have to pay attention to different health issues. And it could produce you probably would have to get rid of the air cooling system, because it would, as I see, this is a mobile thing.
Yeah, this prototype is only mobile, but there is a possibility that you can place, for instance, a radiator outside the house. So, like an air conditioner, you can place on the wall.
Yeah, this is an interesting issue, because you cannot just put something into the surgery room which is collecting air from different areas, and it will just pile up the dust in itself. Therefore, it will be able to put in the surgery room as well.
Yeah.
All right. This is a known issue.
Yeah.
In this project. Thank you.
Okay, let's thank the speaker again.